Okay, we're going to finish off our last topic for graphing, and we're going to look at symmetry today. And symmetry is probably not overly useful when it comes to graphing, but in some cases it helps. If we know a graph is symmetrical, it might allow us to sort of figure out coordinates that we wouldn't normally have. So for example, on this quadratic, if we knew this coordinate and we knew that it was symmetrical, well, obviously the one right across from it would be the same coordinates. So it might make the graph a little bit easier to draw or to see if there's patterns or whatever, but other than that, it's not overly that important. What we are going to do today, though, it will help us sort of remember a little bit of things from Math 30-1, which is good. So our first type of symmetry we're going to look at is called even symmetry, and it involves dealing with a horizontal reflection. So if you took this graph and you did a horizontal reflection, this graph would be the exact same thing. So instead of calling it a horizontal symmetry, we're going to use the word even, and we'll see why a little bit later on. Odd symmetry is a little different. It's not just a vertical reflection. Like if we took a vertical reflection of this graph, it would look something like that. So definitely vertical symmetry isn't there. But now if we did horizontal reflection, it would be the same. Okay, so odd symmetry is sort of a combination between horizontal and vertical. And maybe that's why we don't use those kind of words. So we'll go through we'll look at a few definitions, and then we will look at some examples. So for example, symmetry, like I said earlier, will it help us sketch graphs? Maybe. If you know half of it and the other half would be symmetrical, it might help. But other than that, it's not really that big of a deal. So we'll start with even symmetry. So even symmetry, we've talked about already, is if it's symmetrical horizontally, but we're going to look at it from an algebra perspective. So if we look at algebra, and you remember from Math 30-1, a horizontal reflection occurs when we take our x coordinates and make them all negative. So that means all we have to do is compare our original equation to the horizontal reflection equation and see if they're the same. If they are, it's even. If they're not, then it's not even. So it works pretty simple. So for this first example on the bottom, if we take the original equation, I'll just write it as f of x just so we can get used to the notation. Now if we make the x negative and we simplify that, you can see that this would simplify now to the exact same equation, right? The negative x squared doesn't change anything because it's squared. So because these two are both the same, then we do say, yes, it is even symmetry. So if we were to graph this equation and we look at the graph, we would see it indeed have horizontal symmetry. So if we try another one, here's a cubic graph. And if we just look at the algebra again, we take our original equation, and now let's make all of the x's negative. The cubic one will change this time, right? Because negative x cubed will still stay negative. Our 2x, negative 2x, will also change because the two negatives would make it plus, but our 4 at the end doesn't change. So now if we compare our original equation to this reflected equation, they are not the same, so this one would not be even. So we'd have no even symmetry. And again, if we looked at it as a graphing perspective, it'd be pretty easy to see that it doesn't have symmetry because it's a cubic graph. So odd symmetry, now that we had a cubic graph, the odd symmetry might imply that cubics should be odd. And that's where the name comes from. It has to do with the powers of the functions. So if it's squared, it typically has even symmetry. If it's cubed, it'll typically have odd, but not always. So when we look at that graph again, let's go back to a cubic graph, something like this. It does have odd symmetry. So some people think of it as being a 180 rotation. So if you took half of this graph and rotated it 180 degrees, it would overlap the other side. Or some people say, if I did a double reflection, if I did a horizontal reflection first, so this graph horizontally would look something like that, then I do a vertical reflection of that new reflection, it would match the original. But it's actually easier to test the two reflections. So if I do a vertical reflection and I would get, in this case, the same graph as the horizontal reflection, therefore they have to be odd symmetry. So what works kind of well is you don't have to do anything differently. We just do the even symmetry first and then continue on to do the odd symmetry. So for this one, if we test the even symmetry first, so take our original equation, let's put a negative in for our x's. So you can see our x to the fourth wouldn't change, but our minus 2x will switch to plus. So it's definitely not even because the two x's are different. So now if we do the vertical reflection, and algebraically when you test a vertical reflection, we just put a negative out front. So for this one, all we have to do is change the entire equation to the opposite signs. So that would give us minus x to the fourth plus 2x. So now if we compare those two answers, they're not equal. So we would say it is not odd. So if the original and the horizontal reflection match, it's even. If the horizontal and the vertical match, it's odd. If neither of those things happen, then we just say there's no symmetry. So let's go through a few examples and we'll see if we can determine whether they're even, odd, or neither. We'll start with some polynomial equations because they're the easiest. So a regular polynomial equation, really all we have to do is look at the power, and that should be enough to help us figure out what's going on. So for this first question, you can see our power is x to the 5, which is an odd number, so we should have odd symmetry. So let's check that out to see if it works. So if we do negative on the inside, that would make our equation 1/2 times negative x to the 5th, which would make it negative 1/2 x to the 5th once we simplify. If we do negative on the outside, that would give us negative 1/2 brackets, oops, sorry, it would be negative 1/2 brackets x to the 5, so that would be the exact same thing. So in this case, it is odd, right? Our two reflections are equal to each other, so because of those two matching, we do have an odd symmetry. So this next one, it looks like we have even powers. We have an x to the 4th, but what happens if there's more than one? Do they all have to be even? Is it okay as long as one's even? Is it just the highest one? Those are the things we got to be careful about. So let's try it for this one. If we do our horizontal reflection first, so that'll turn all of our powers, all of our x's negative. So again, it won't matter on the x to the 4th because it's an even power. It won't matter on the x squared, and the 4 isn't going to do anything at all, so that one should be okay. We should get the exact same equation, so that one should be even. So the only issue is you got to make sure all of the powers are even, and even this 4, a lot of people think, well, what's the power on the 4? But we could always think of it as like x to the 0. 0 is an even number, they're all even, it will be even symmetry. So if they're all odd, it should work the same. So in this case, I've got 3x cubed, 4x. You can think of the 4x as being x to the 1. So those are odd, so maybe odd will work. So let's try it. So if we do our negative horizontal reflection, we have, it'll be a negative 3x cubed. It would change it to plus 4x, and our 2 would stay the same. If we did a vertical reflection, that'll change all the signs, so we'd have negative 3x cubed plus 4x, but it also changes the 2. So because those 2's are different, this one will be neither. It's not even or odd. So for this to be even, all the powers have to be even, so the 2 is considered an even number. If it was to be odd, we would need another odd power on here, so it'd have to be something like x to the 1, 3, or 5. It also works with fractions. Actually, fractions are slightly different, but by itself, if this was like x to the negative 1, that would be considered odd as well, because the negative on that would indeed change the symbol the way we need it to. So basic polynomials are pretty straightforward. If they're all even, it's even. If they're all odd, it's odd. If there's mixtures, then it's going to be neither. So let's go through other functions that we've looked at over the last few courses and see if we can identify whether these have symmetry or not. So you can either look at it from a graphing perspective and visually determine, or we could do this same, put the negative in where the x is and go that way. So for this first question, let's look at the graph first. If we look at the graph of square root of x minus 2, that's just going to be a regular square root graph that goes starting at 2 and goes upwards to the right. I kind of have it curvy, but close enough. Okay. So just by looking at it, we can see there's no symmetry. We have neither, right? There's no, if we reflect it vertically or horizontally, it's not going to look the same. Definitely, there's neither. And if we did it algebraically, you should see that it would be the same. So if we put a negative on the x, that's a different equation, so it's not even. If we put a negative out front, that's a different type of reflection, so that's not the same. None of these equations are the same, so that does show that it would be neither as well. For the second one I got that has x squared on there, this one will be slightly different. So let's try it as a horizontal reflection first. So in this case, it would give us the same equation, so that should be even symmetry. And if you think back to Math 30, these kind of graphs are what we typically called our like seagull graphs. So x squared minus 4, the original graph would look something like that. So remember, when we square root it, we get these little curves going outwards, and those are horizontally symmetrical to each other. So it does make sense that it would have even symmetry. Other than that, all other square root graphs will be no symmetry at all. It's just these kind of square root ones will be the quadratic seagull type would be the same. Other kinds of functions, logs and exponents, generally there's no symmetry at all, because remember, whether it's a log or an exponent, they basically just start along the asymptote line and curve up. So it doesn't matter if it's log base 5, log base 4, whatever. In this case, we're going 5 to the left. So that really doesn't matter because it's just going to shift it over left or right anyway, but it's still not going to be symmetrical. So definitely no symmetry for logs, and exponents pretty much the same thing, right? Our exponent graphs look something like that. There's no symmetry for those either. So logs and exponents, pretty simple, none. The next type of function that we got to consider is trig. So again, we could do this from a graphing perspective, and it's probably easier as a graph. So if we graph sine x, remember it just kind of makes our wave something like that, and it continues in both directions. So that would be our sine graph. So if we did a horizontal reflection, it will not be the same. It would look something like this. So that's not the equal graph. But if we did a vertical reflection, the horizontal and the vertical should match. So for a sine graph, we should have odd symmetry. If we were going to try to prove it algebraically, we would have sine of negative x for our horizontal reflection, and we'd have it as negative sine x as our vertical reflection. Now, it's hard to prove that those are equal to each other mathematically. We'd have to go to the unit circle where we have, let's suppose we have 30 degrees. So our coordinate at 30 degrees is 1/2. If we did negative 30 degrees, our coordinate would be negative 1/2. So if we plug those into our formula, they should be the same. So the top one is sine of negative 30 degrees. So that's our bottom coordinate, that's negative 1/2. The second one is saying, let's just go negative of whatever that coordinate is. So it'd be kind of like negative brackets 1/2, which are the same thing. So it does work, but it's a little bit more complicated where we have to use unit circle or trig identities or something like that to prove it. So probably for trig, the simplest way is just look at the graphs and try to figure it out that way. With trig, usually stretches don't make a difference. So if we do a vertical or horizontal stretch, that won't affect symmetry, but translations would. We start moving these things up, down, left, or right, they will no longer be symmetrical. So a cosine graph, let's sketch this one. If it's 3, it's going to be taller. And if it has a horizontal stretch of 1/2, that would just shrink things skinnier, but that shouldn't affect symmetry. So our cosine graph should look something like that. So if we did a horizontal reflection, it should match, right? Because that is centered right along the y-axis. So in this case, we should have even symmetry for a cosine graph. And the last one I got, a tan graph. We didn't do much of those in Math 30, but if you look on a graph, it would look something like this. So we have these asymptote lines, and the graph just sort of repeats itself, something like that. So this one, you can see if we do a horizontal reflection, it wouldn't be the same, right? Because it would kind of make sort of X's. So it's definitely not horizontal, but if we did vertical, our horizontal and our vertical would overlap each other. So based on that, it would be very similar to our sine graph where we'll get odd. So generally, if I get a trig question, I would just graph it from looking at the graph and looking at how the reflections would look. You should be able to figure those out pretty easily. The last type that we do have to worry about symmetry for are rational graphs. So remember, if we have a basic rational graph, something like that, we would have odd symmetry. But if we have more complicated ones, they possibly could have even symmetry or no symmetry at all. So the best way to do it is just do our tests like we did with regular polynomials, and it should work. So for this first one, you can see we have even powers on the top, we have even powers on the bottom. So logic would say that even divided by even should be even. So if we actually do our horizontal reflection, let's see what happens. If we put a negative in for our x's, because they're even, they won't change. So that does make sense. All of our even powers will stay the same. So even divided by even will give us an even symmetry situation. The next example I got, you can see it has odd powers on the top, odd powers on the bottom. So is odd divided by odd going to be odd? I don't know. Let's see. So if we put in a negative for the x's, in this case it will switch our signs. So all of our signs will flip if they're horizontal reflection. We look at those two equations, they don't look the same, but they actually are. Because we have negatives everywhere, we could simplify this by factoring out a -1 on the top. And we could even take out a negative on the bottom if we want. And you can see the negative divided by negative would cancel each other out. This equation is exact same as the original. So, oops, it's not odd. It ends up being the exact same when we do our horizontal reflection. Therefore, it's even as well. So even over even gives us even, odd over odd gives us even. The next one I got is even divided by odd. So we have one of each. And it shouldn't matter whether it's on the top or the bottom, we should get similar results. So let's try it again. If we do our horizontal reflection, the top won't change in this case, but the bottom will. So it's definitely not even. If we tried our vertical reflection, and here's where we got to be careful. People make mistakes with this. So remember with fractions, if I told you we have -3/5, we either write it as -3 divided by 5, or you write it as 3 divided by -5. Either of those two versions are okay. What we can't do is you don't write it as -3 divided by -5. Otherwise those negatives would cancel and we're right back to what we did in the previous example. So for this one, to make it negative, we either make the top negative. So let me write that. And we leave the bottom the same as it was originally. Or we could make the bottom the same, or the top the same, and make the bottom negative of the original. So either of those two cases would be correct. So we want to compare it to the one we did previously. So our even horizontal reflection, it won't match the first one, but it will match this bottom one, right? Because if we put a negative on the bottom, those then would be the exact same thing. So that means since those are equal, we do actually have odd. So even divided by odd, or odd divided by even, will give you odd symmetry. The last example I've got is we've got neither on the top and we've got even on the bottom. And it doesn't matter if it's neither over even or neither over odd or flipped the other way around or neither over neither. As soon as we have neither symmetry, basically that wipes out everything. Because if we do our horizontal once again, our top x squared doesn't change, but our 4x does. But then the 2 doesn't change. And then on the bottom, nothing changes. So because our 4x on the top switched to negative, it's definitely not even. if we make one whole thing top or bottom opposite, so if I did negative x squared minus 4x plus 2 on the top, that's not the same, so that doesn't work. Or if I did it the other way around, made the bottom opposite, that doesn't match the original either. Okay, so our original doesn't match horizontal, so it's not even, and these two don't match, or those two don't match, so therefore it's not odd either. So in this case, we have neither even or odd symmetry. And that's it. So rationals, you got to be a little bit careful with. Trig, kind of difficult, so basically look at the graphs. Every other scenario basically will be a polynomial where we can just look at the powers and determine whether they're even or odd. And that's all for today, and we're actually done the unit. So we'll finish this off, review a little bit, and we'll be ready for our unit test.